on Bayesian modeling, inference, prediction, and decision making. A few new things on the web page. We now have the videos of all of the first 7 days of the class available down in the video section. Reminder that we'll be continuing to meet here at this Beacon Rock room for weeks 9 and 10 as well, next week and the week after. I've added some new material under the various weeks of the course. I've split off week 8 from week 7. It originally looked to me as though week 8 would be like a continuation of week 7, but there's enough new material that they should have, each should have its own category. And I posted the extra notes, the handwritten notes from the document camera up here from last time. And the new things under today's date, we'll be talking today about specific details about how to do Bayesian nonparametric modeling. And there are 2 sections of that, of those lecture notes. Also, last time we looked at Bayesian model averaging with a package from CRAN called BMS. Today I'm going to show you how to do it with a more general package called BMA, and we'll be doing that, in fact, pretty soon. So I've posted a tutorial for how to use the package here, and the tutorial is quite easy to read. And I've also posted the CRAN user guide for the package BMA, which is much less easy to read, but at least it has some examples in it that you could use as templates. Also, either today or next time, we'll be talking about some material in a paper that one of my students, Milovan Krnjaic, and I are working on. Despite this looking like it came out in Bayesian analysis in 2010, it's actually still under revision for future submission. We withdrew the paper from Bayesian analysis because we didn't like the way they were treating us editorially. We're still working on that. So those are going to be some ideas that we'll be talking about, either possibly some today and also possibly some next time. I forget if I mentioned this last time. I put an article under week 10 that is meant to be a kind of overview of the entire course. I was invited to write an encyclopedia article on Bayesian statistics for something called the Encyclopedia of System Complexity, I think, or some name like that. Complexity in System Science. And so you could begin looking at that now at your convenience to bring together many of the things we've been talking about, or you could wait until week 10 or thereabouts to use it as an overview of everything we have done at a rather high level, with the course providing many details about how to actually do this stuff. And there's some new R code as well. I've added the Bayesian model averaging code to use the package BMA, which is in some senses better than the BMS package. And I've written some code to do Bayesian nonparametric modeling in using Dirichlet process priors in R and polyetry priors also in R that we'll be looking at today. And later today, we'll look at, there's a model comparison tool called DIC that the Winbugs people like a lot. It stands for Deviance Information Criterion, and it works under some conditions and doesn't work well in others. And I have an example of a situation where it behaves rather badly. So those are some of the new things. And I think a good place to begin today would be to get back out the, oops, not that one. Get back out the, here we are. The lecture notes from last time, as a reminder of how far we got last time and where we are now. Last time's discussion was mostly at a rather high level in terms of strategy rather than tactics. And it was more theoretical than some of the previous weeks. I'm hoping to balance that today by showing you a number of actual details with examples on how to do the coding and how to actually interpret the results. So if you felt that last time was more theoretical than you like, that's okay, because I'm going to try to balance it out so that by the end of last time plus this time, you'll feel that there's a good balance. So we were in the process of, we began by looking at a method for laying out definitions and axioms and implications from those definitions and axioms to create a kind of logically, internally consistent description of almost the entire field of statistics. And we came around to the idea, at least from the Bayesian point of view anyway. We talked about different forms of probability, the original classical Fermat-Pascal approach, the Kolmogorov and John Venn and Ricard von Mises approach based on the frequency story, and the Dave Finetti and Richard Cox story based upon Bayesian reasoning that we've been looking at mostly this entire course. And I focused especially last time on Richard Cox's way of looking at things because I find it to be quite natural to base all of my own thinking on, whether my problems be scientific or decision-making or have a business character or whatever's going on. I think the fundamental thing here is that, as we agreed last time, step one, statistics is the study of uncertainty, how to measure it well and how to make good choices in the face of it. Step two, uncertainty is a state of incomplete information about something of interest to you. Therefore, step three, statistics is about helping you quantify your information about something. And so, and this is the approach that Richard Cox took, that probability is a quantification, I'm on page 12 now, of the part 5 of the lecture notes. Probability is a quantification of information about the truth of one or more true-false propositions, and we have to constrain that quantification to obey a set of axioms that guarantees that you avoid saying silly things like the probability of rain is 0.7 and the probability of no rain is 0.4, adding up to numbers bigger than, some being bigger than 1, for instance. So we try to guarantee internal logical consistency, and Richard Cox does that for us. And we found that a bunch of corollaries of his theorem basically derives the basic rules of probability, but not from axioms that are artificial like Kolmogorov did, but from basic statements about how uncertainty ought to behave when you're just thinking about the world as a scientist or a person who's curious about the world. So he gets out this remarkable theorem based on solving functional equations, and the usual rules of probability come out, and a whole bunch of other corollaries in which we saw, for instance, that it was natural when you're talking about an uncertain theta that lived on the entire real line. It was quite natural to be constructing cumulative distribution functions and densities that describe your uncertainty about that thing, even though that might look like random variables in the Kolmogorov way. In fact, there are no random variables in this approach. Instead, all that's going on is you have uncertain things, let's call them theta, as we did before, whose uncertainty can be summarized when the set of possible values of theta lives on in the real lines or some on the real line or some k-dimensional generalization of that, can usually be usefully be summarized with CDFs and densities. And so that got us to being able to talk about probability distributions like I'm showing here on page 19. So we discover as part of Cox's theorem that we are required, if we want to use his theorem, to arrive at logically internally consistent conclusions. We're required to specify 4 ingredients, 2 of them for inference and prediction, and 2 more using those inference and prediction tools, plus 2 more that are needed for decision making. Namely, firstly, for inference and prediction, the thing we've agreed to call the prior distribution, and then secondly, the thing we've agreed to call the sampling distribution, which gets turned into the likelihood function. And then once we specify, in addition, the action space over which you're deciding, among which you're deciding various actions, and a utility function that maps from actions and the unknown down to the real line and quantifies rewards, costs, and benefits of behaving in a certain way when the true value of the unknown thing is something or other like theta. And it turned out in this framework that there was 1 equation for inference, which we recognize as Bayes' theorem, 1 equation for prediction, which involves predicting future data. I'm on equation 3 now of page 20 of part 5. It requires taking a weighted average of the predictive distribution if you knew what theta was, weighted by the posterior probability distribution for theta. And the predictive distribution for what the data would be in the future, given that you know what theta is otherwise recognizable as what we've been calling the sampling distribution. Yes, please. Any of you who would like to think about theta or d star in future data as a random variable, it's okay with me, because if you think in the world of random variables, then you're quite naturally in the world of placing CDFs and density functions on those random variables to summarize your uncertainty about them. It's just that from a strict point of view in terms of what you need in the way of machinery, the Richard Cox approach does not need any random variables. And in fact, they aren't even the same as Kolmogorov's random variables, because Kolmogorov's random variables, in his world, the operator P of A given B, the A and the B are sets that are subsets of the sample space omega, and we don't have sets in Richard Cox's approach. We just have true-false propositions. But if you want to think of things in parallel in terms of random variables, because that's what you're used to, that's okay with me. It won't affect your being able to quantify uncertainty. So we have one equation for inference. We have one equation for prediction. Thank you very much. And we have one equation for optimal actions, namely to maximize expected utility where the expectation has taken over all of your information about theta at present, which is your posterior distribution for theta, given the data and the prior information. So that's at a pretty high level, and it justifies all the stuff we've done up through weeks 1 through 6, namely, if you're prepared to specify those 4 ingredients, the ones that are listed there on page 22, namely the prior and the sampling distribution and the action space and the utility function, then you have a logically internally consistent way to reason, and nothing bad can happen to you like happens in the frequentist approach, where sometimes your estimates of quantities that have to be positive go negative and other unpleasant things. So this is a big if. If you give Richard Cox those 4 ingredients, then out comes the 3 equations that tell you how to behave in a logically internally consistent fashion. And pretty much all the rest of the course from now on out is going to be either about principles on how to specify those 4 ingredients, or else actual examples of doing so. Because now, essentially, that's the heart of the Bayesian story. Now that we've spent 6 weeks or so understanding how to speak the Bayesian language and looking at special cases of it in simple settings, now we're going to try to open the doors wide. And I'm hoping that as a result of last week and this week and weeks 9 and 10, you will start feeling as though you're well equipped to begin thinking about this way on your problems, the ones that you came to the short course with. And in fact, those of you who might like to see me featuring Bayesian solutions to your problems in week 10, where I'm going to be going through a series of case studies, can please get in touch with me by email, and we can talk about the suitability of your problem for that sort of thing. Your problem could have a design character. That would be interesting to talk about. It could have an analysis character where you already have data, in which case you would need to be able to share the data with me, suitably sanitized or whatever might be needed to deal with confidentiality issues. And then you would, of course, have to share fully with me the context of the problem so that I could help in the process of specifying those 4 ingredients. So basically, we are now on the bottom of page 24 as a summary. Inference and prediction require us to specify those prior and sampling distribution. Ingredients decision-making require us to specify those same 2 things plus 2 more, the action space and the utility function. We do not, however, have a natural progression from principles to axioms to theorems, as was the case in Cox's theorem, that shows if you reason in along that natural progression, then there's one and only one way to behave. That's essentially what Cox says. You've got to use the Bayes' theorem for inference, you've got to use the prediction equation for prediction, and you've got to maximize expected utility for decision. What we agreed on last week, I think, is that except in rather rare cases, if you think of what's happening in terms of Bayesian model specification as the process of, so we've agreed to call the model your model for your uncertainty about theta. We agreed to call that the collection of those 4 ingredients. So theta given the background information, that's your prior predictive distribution, people sometimes call it, otherwise known as your sampling distribution. The action space, which I'll write in a different way than on the screen because I don't make that symbol for calligraphic A very well. And then the utility function that maps from actions and theta values to the real line. So there's your model. And essentially what I'm saying is we start with a real-world problem. So here's the real world. Let's call the real-world problem script P, not to be confused with script P as in a population of interest to us. That's a symbol I used earlier in the course. And the whole trick of applying the Bayesian story in real problems is in working this thing out here. Let's call that whole thing your model for your uncertainty. What is the nature of the mapping from the real problem to those four ingredients? And the essential difficulty for us is that except in rare cases, and I'll create a document for next time that summarizes all of them that I know about, except in rare cases, this mapping is not unique, even among reasonable people. Reasonable people. Different reasonable people working on the same problem might start with the same problem and end up with a different four ingredients. Even if, for example, we agreed that there was little information external to the present data set about some quantity theta, you and I might choose to use different diffuse priors to quantify that information base. People use different sampling distributions from each other all the time on the same data set. It would be great if you and I were working on the problem together from a decision point of view and we could agree on the action space, but actually one of us might turn out to have a more comprehensive action space than the other one. There's plenty of potential disagreement about utility functions because in particular, from your point of view, working on the problem, trying to make a decision, your utility function, which quantifies your values essentially, your utility function may very well be quite different from mine. And then that's another whole problem that we haven't talked about yet that I'll try to speak about a little bit on week 9 or week 10. How do you make optimal decisions, not one person at a time, which is what the maximizing expected utility result says how to do, but how do you make optimal decisions when the you that's trying to make the decision is a collective of two or more people? Often that collective will turn out to be in partial cooperation and partial competition. And that means it's going to be very hard to find a single utility function that everybody would agree on. This is a deep and difficult open problem in Bayesian statistics, and that means it's a deep and difficult open problem in economics and all the other fields that try to make decisions in rational ways. I have an idea for how to make progress on that I'll share with you toward the end of the course, but I'm not going to get to that. This week we're still talking about inference and prediction. Given that this mapping is not unique, some of these mappings, so you could imagine different people might have all sorts of different maps, all sorts of different paths from the problem over to the model. Some of them might even be paths that looked a little bit circuitous, as my father used to say. Now the question becomes how characterize I'm having trouble spelling on the fly today. I haven't had a lot of sleep lately. So have you ever noticed when you don't have a lot of sleep, it digs into your ability to spell? Characterize. How characterize the good mappings? If, of course, there's one and only one mapping, then it's the best by definition, right? But there will hardly ever be just one mapping. And so now, the rest of the course, we're going to try to focus on the issue of how do you arrive at good models for your data. And also, there's some other, what you might call ancillary questions that are connected to that. Namely, if here we have how characterize the good mappings, here's another question. How can you tell when model 1, the result of mapping 1, let's say, how can you tell when model 1 is better than model 2? And in fact, those of us in the room with a computer science bent would probably recognize the following reasoning. As soon as we admit the possibility that there's more than one model for our given problem, then that opens up the doors to a model space, and it suggests to us that it would be great if we could come up with some sort of algorithm for moving around in model space and visiting a model for a moment and discovering how good it is, being able to see if it's better than the previous model, and if so, either discarding the previous model or just adding it to the archive of models we've looked at so far, and then moving on from there. Today, if there's time today, certainly next time, I'll present you such an algorithm. Although it has crucial steps in it that at present no one knows how to automate. And so we do not yet have a robot, although it would be really nice. I'm not talking about giving over the entire task of modeling to robots, because at the moment we don't know enough about how we as humans build our models to be able to do that. But suppose I offered you a robot, and besides, you might not want to give that responsibility away to a machine. But what if I offered you a robot that had the following character? You finished up your thinking on a particular day, and the last thing you did before going home for the night was you said to the robot, okay, this is where I am right now, robot. Please try to find me 50 or 100 more models that I should be thinking about by tomorrow morning that seem like they have a chance of being interesting to look at. And now you go and hang out with your friends or your wife or whatever, and you have a nice sleep, and you come in the next morning, and the robot says to you, okay, I found 38 models that you haven't thought of yet that you ought to look at. Wouldn't you like to have such a robot? I think the answer is pretty much everybody would like to have such a robot. And I will show you a skeleton of how to move toward such a robot in the work today, or possibly next time. Making the robot operational, in turn, involves figuring out how to make operational several key questions. I know how to operationalize all of them but one. And that one is the NP-hard one, for those of you who are computing kind of people. There still is an NP-hard question in the middle of any attempt to build such an algorithm, as far as I can tell. Okay. Returning now to page 25. What I'm going to do, and what I've started to do in this document, is to share with you some principles for arriving at good models. In fact, I made a definition last time of what constitutes an optimal model specification. So that, according to that definition, if you buy it, there is a path forward in which you start with a problem and you end up with the best model. But unfortunately, it turns out that it's quite rare that you can actually satisfy that definition of optimal model specification. And so instead, today I'm going to focus on what to do when you can't satisfy the definition of optimal model specification. So I gave you a definition at the top of page 27. Because it's a bad idea in the Bayesian paradigm to condition on things that are known to be false, because that's the probabilistic equivalent of dividing by zero, it seems like a good definition would be like the one on the top of page 27 of part 5 of the lecture notes. Namely, in model specification, optimal specification means coming as close as possible to the goal of conditioning only on propositions rendered true by the context of the study and the design of the data gathering process, and perhaps anything else that you regard as so essentially true that there's no need to question it anymore, such as that you are alive in this instant and that you're pretty darn sure the sun will rise tomorrow, and all those things back there that we are keeping in our set script B that we don't make explicit. But in the way of making explicit things we're assuming to go along with the background ones that we never even talk about, I'm pretty sure, at least I'm hoping, to be pretty sure that I'll still be taking breaths 10 seconds from now, things like that. You know, we have all these stuff that we're conditioning on right now. In addition to all those ones that are way in the background, I would like to add only propositions to that are guaranteed true by the context of the study and the design of the data gathering process. So for example, when you're gathering a bunch of data from a random process that's generating numbers on the real number line, if all I tell you about it is, for instance, that I'm measuring quality of care scores for people at a particular hospital by choosing patients at random and building quantitative scores that measure the quality of care, along comes my desire to slap on top of the basic story of the problem I'm working on the idea that if I knew what mu and sigma squared were, those numbers would be conditionally IID draws from a normal distribution with mean mu and sigma squared. Now, from what I told you of the context of this problem, these are just patients, let's say, with a heart attack at one particular hospital, the Dominican hospital. Is there any reason why it would follow automatically as a truth that arises from the context of the study and the design of the data gathering process that the one and only one sampling distribution for that data set should be the normal distribution? Just because the numbers have to live somewhere on the real number line, and my uncertainty about them is continuous, and that's good. The normal distribution is continuous. But we know that there's many, 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 many continuous distributions. And why the Gaussian? Well, people tend to slap that down because it's a familiar person to them in terms of these uncertainty people walking around in your head and so on, and then work base calculations on that. But when you do that, of course, what you're doing is instead of trying to learn about let's say theta is the population mean quality of care at the Dominican hospital for heart attack patients in the year 2012, for example, just to have a quite concrete population thing to talk about. What we want is the posterior probability for theta given the data and the background information, where the background information is driven only by context and design ideas, problem context and data gathering design context. We don't want not P of theta given D and B and the assumption, the true-false assumption that yi given, the true-false proposition that yi given where the data vector is y equals y1 through yn, the true-false proposition that yi given mu and theta are like IID draws from a normal distribution with mean mu and sigma squared, mu and sigma squared unknown. So that is a true-false question, or rather a true-false statement in Mr. Richard Cox's world. And if I make calculations conditional on the normal distribution, that's really all I've got when I'm done. I have learned about theta. Theta might turn out to be mu, for example, in this model, for instance. Given this particular true-false proposition, if that were true, then theta would be mu. But more generally, if I had some other model for the data, theta wouldn't necessarily be mu. It's just the population mean. So do you see the difference between item star right there and item star star? Star says, let's try to build a model that conditions only on stuff that was definitely made true by the problem context and the data gathering process. Star star says, well, let's toss in the extraneous assumption of normality that is not based at all on the problem context because the normal distribution is not in any sense forced upon us, and then hope for the best. And that's what people almost always do in real statistical work, with the possible exception of having arrived at that normal distribution by cheating, as we talked about before. You look at the data and you say, oh, that looks kind of normal, so I'll slap the normal assumption in there. But we know now from our discussion last time that that has a circularity to it in which we've used the data twice. We use the data to specify something to condition on, and then we use the data further to specify something else to condition on, namely the data values. So we're pretending that the data, it's okay for the data to inform this part, the D right there, and it's also okay for the data to inform this part. And the something for nothing bell should be ringing in your head. You've used the data twice. So today we're going to talk about, we already talked last time about one method to try to do a better job than simply hunting around in model space with your entire data set and then pretending you knew what the right model was when you conclude your hunt. We talked about one way to improve on that last time. It was called Bayesian model averaging. And I'll now show you another way to do Bayesian model averaging inside R with a different package than the one we looked at last time. And this time I'll show you on the same data set as last time. And I'm working now between now and next time to come up with a much more interesting data set. I have a data set in which we're trying to predict ozone concentrations in the LA basin on each of 365 days in a particular year back in the past from about 15 or 20 meteorological variables, and when you bring in all the various things that might be relevant, like quadratic terms and interactions and so on, we end up with a data set with about 300 or so observations and about 75 predictors in it. And 2 to the 75 is a really big number as the set of all possible subsets of those particular predictor variables. And so I'll bring that data set in next time, and we'll fire up an MCMC on that and see how we could go about the process of moving around in sample space, in model space, trying to find good models by visiting them for a moment and seeing how good they seem to be, which is the contemporary way to try to solve problems like that. Okay, so that's Bayesian model averaging. I'll get back to it in a minute. Then another way is, I'll just jump ahead a little bit. Another way is on the bottom, page 32. Another way is Bayesian nonparametrics, and I'm going to show you some ideas of how to do that as well. Oh, thank you. I'm on the wrong place. Thank you. I'm on page 32 now. of the part 5 of the notes. Bayesian model averaging BMA at the bottom part of that page, one possible approach, Bayesian nonparametrics, another possible approach, and a method that I call calibration cross-validation. And time permitting, we'll talk about that today as well, and certainly we'll talk quite a bit about it next time. Before we got to that slide, though, I shared with you one particular principle for trying to move toward good model specification. Last time it was called the calibration principle. And those of you who come to this course from a frequentist perspective probably bought into this principle without anyone even having said it out loud to you before you came here. And if there were any Bayesians in the room before the course started, I'm trying to argue that Bayesians should be equally compelled by this principle as frequentists, because there's a basic issue here, namely, I'm trying to develop methods for separating signal from noise, where signal means something that really would exist if I went out and replicated my experiment over and over again. The signal would persist across those repetitions. And noise means something that looks like a signal, but it wouldn't persist across repetitions of the experiment. For instance, did we talk about cold fusion last time? I forget if we've ever talked about cold fusion in here. You ever hear about cold fusion? These guys from Utah claimed that they had figured out a way to produce energy via fusion at ordinary room temperatures on the Earth's surface, rather than the enormous temperatures, very, very, very hot temperatures at the core of the sun. If that were true, it would have created an instant revolution of everything we know about how to think about energy, because it would have made an infinite supply of energy available to us. All you have to do is break open hydrogen atoms, and you now have as much energy as you want. And all the oil companies would have gone bankrupt, which would not necessarily be a bad thing in any way. And life would have really, really changed. But as soon as they announced it, everybody around the world that was interested in this immediately started trying to replicate their findings, and they discovered that it was not replicable. And these guys had to kind of slink away and say, oh, I'm sorry, we tried to announce what we thought was a signal, but it turned out to be noise. The terminology I'm talking about now. They thought cold fusion at room temperatures existed. That would have been an enormous signal and a really interesting one, but it turned out to be noise. Instead, they didn't analyze their data well, and they didn't set up their experimental equipment properly either. We're in the world. All of you are solving real problems collaboratively with other people, or one by one, practically every day in whatever you do in your work. And by the way, you're also solving problems like that every moment of your existence outside of work as well, trying to decide which way to drive into work today based upon the weather and what you hear on the radio about the nature of the traffic, deciding what to eat for lunch today. I mean, there's all these decisions that we have to make all the time, and they're all in the presence of uncertainty, because you almost never have all the information you need to be able to figure out what to do optimally. And so we're all trying to solve problems all the time. Wouldn't you agree with me that if the problem has a statistical character to it, namely when you start measuring the thing you're interested in, you discover that you're measuring signal plus noise, which is what most often happens, then therefore you need a method for separating signal from noise. Wouldn't you agree with me that it would be good to know something about the characteristics of that method? In other words, how often when no signal is there, does it say the signal is there? That's a false positive, as we're going to call it. And how often when signal is there, does it incorrectly say it's not there? That's a false negative. So we would always like to be able to say something about the false positive and false negative characteristics of any method we have for separating signal from noise. And that comes down to answering the basic scientific question, how often does your method for analyzing data get the right answer? And a good way to answer that question is to build environments, simulation environments, where you know what the right answer is, and see how often your method recovers known truth. And so that led me to the calibration principle here on page 28 of part 5. In model specification, we should all pay attention to how often our methods get the right answer. And a good way to do that is to create situations in which you know what the right answer is, and seeing how often your methods get back the right answer. That just seems to me quite basic. And in fact, it's even more basic than the Bayesian frequentist so-called schism, because it's an even deeper scientific concept than issues about what kind of probability you use to think about the world. Frequentists, as I said, already buy directly into this principle, because the process of paying attention to how often you get the right answer is an inherently frequentist process. Bayesians, I argue here, ought to pay attention to it as well, because if you write down a utility function over your entire career as a person trying to separate from signal from noise, and you give yourself a bonus for being well calibrated because you want to be well calibrated according to I should say I assumed another axiom, namely the one at the middle of page 28, namely that you want to help positively advance the course of science, and repeatedly getting the wrong answer runs counter to this desire. If you buy into that axiom, and I think everybody does pretty much, then it follows directly that you ought to pay attention to how well calibrated you are, because if you end up getting the wrong answer a lot because you're badly calibrated, then people won't work with you anymore, and you won't be able to actually help advance the course of science or business or whatever it is that you're interested in. So I suggest that all of us should be prepared to take a broad perspective over our entire careers, not just the one problem we're working on now, and pay attention in a broad sense to how often we get the right answer across all those different problem-solving opportunities. And in fact, I suggest that we ought to be building utility functions where we give ourselves a bonus for being well calibrated. I'd like to look back at the end of my career, like I had in that artificial dialogue with St. Peter, and find out that actually most of the time when I said there was signal there, it really was there. And most of the time when I said it was just noise, it really was noise. I'd like that to be true. That helps me to be a good scientist and a good collaborator with other scientists. And so you can actually make Bayesians, if Bayesians buy into this logic I'm just sharing with you here, and I don't really see any way out of it, that makes Bayesians interested in calibration as well. That's actually quite a sharp idea for some people, because there are some people called subjective Bayesians, sort of hardcore subjective Bayesians. One of them is a good scientist at Carnegie Mellon named Jay Cadane, for instance, who don't really think that calibration is something he has to care about, because he says you're never going to actually run into a situation in your life where something is repeated over and over again exactly the same way to see what would happen across those hypothetical repetitions anyhow. But then I say to Jay, well, what about those repetitions of solving problems across your whole career? Wouldn't you like to be one of those scientists who at the end of your career would have mostly right answers across those repetitions instead of mostly wrong answers? And Jay says, let's go have a beer at that point. He has no reply to that. In other words, it threatens him as a subjective Bayesian, but he doesn't have a reply to it. And so I think subjective Bayesians need to be aware of this stuff as well. So here we are. So there's the calibration principle. And if you ever listen to this, Jay, because this is posterity now, I understand, it's going to go into the ISBA archives. If you ever listen to this, Jay, and you disagree with what I just said, please ring me up and we'll have a good conversation about it, preferably over beer or wine or whatever. We started talking about model uncertainty, the fact that you don't know what a good model is or the best model is, in the sense of this mapping from your problem to your ingredients. That got us onto various ways of trying to, quote, solve the model uncertainty problem, page 31 now. And we saw that people used to solve the problem by ignoring it. And so on page 32, I reminded you of how many people used to behave and still behave when they're in a hurry. Namely, you grab your whole data set and use it to conduct a search among possible models, and then you often settle upon a single apparently best model, M star, arising from that search, because it's hard to juggle more than one model at a time. When I say a model, I'm not talking about something like a sampling distribution that contains in it exact specific values of the parameters. I'm talking about the class of sampling distributions corresponding to, let's say, the normal distribution with unknown mean and variance. So that's a sampling distribution which still has lots of degrees of freedom in it, because you can go out and ask the data what the best mu is and what the best sigma squared is. So we hunt around in the data for the best model structure, you might call it, not yet identifying the parameters. And then we draw inferences about the thing that's unknown to us, pretending that we already knew somehow that the model that we found through the search process is the same as the data generating model. And of course, the something for nothing bell tells us that that's probably a bad way to go, and that the reason that's not so good about it, the thing that's not so good about it, is that it tends to, having used the data twice, you're pretending that you know more than you do, and that's going to end up directly corresponding to having uncertainty bands that are generally narrower than they should be. And so, as a general principle, we're headed toward acknowledging model uncertainty will generally result in wider uncertainty bands than the ones we have now. And that's not a very good message, particularly in business realms where people are sometimes rewarded for how narrow their intervals are. And in fact, people's bonuses are sometimes increased when they figure out a way to make their intervals narrower. But of course, we can always go back to our bosses and make our intervals narrower just by the artifice of taking the intervals we have now and dividing their length by 2 just because we wanted to make them narrower to get our bonus. And of course, the boss, if he or she is on the ball, will say, okay, your intervals are narrower now, but how often do they get the right answer? And if you made them artificially narrow just to get the bonus, and now we find out that your alleged 95% intervals only include the right answer 36% of the time, you're fired. So what we want is intervals. So I basically, we're in a situation where we have a dilemma. Do you want to present to yourself and other people narrow intervals that turn out to be artificially narrow because they're not well calibrated, or wider intervals that are well calibrated? And you got a choice, really. You really have a choice. If you prefer to ignore the model uncertainty problem, then you will be in that former camp, unfortunately, more often than you would like. So we're in today and next time and the following time, among the various things we'll be talking about is how to do better than that, this M-star approach, I'm calling it, where we put all our eggs in the basket that was arrived at by one single search on the same data that was used to learn about the parameters conditional on the search. So 3 different ways to do better than that. BMA, all this alphabet soup here at bottom page 32, BMA, BNP, and CCV. And I'll interrupt myself now from this narrative and go back to talking about Bayesian model averaging because, as I mentioned, I have a new bit of code to demonstrate to you. So let's go back to the course webpage. Yes, please. Well, yes. So let's talk that through. He said, is there a danger in trying to assess the calibration of your models that you might end up sacrificing robustness with respect to situations you haven't thought of? And so let's unpack that for a minute. The method I'm suggesting for checking calibration is to create simulation worlds in which you know what the right answer is and see how often your method for separating signal from noise gets the right answer back. If you only do that once with respect to a situation that looks just like what seems to be going on in your data, and then you wait 6 months and gather more data, and the thing you're trying to study has changed, for example, then you will have been well calibrated on the past, but not necessarily well calibrated on the future. And so he's trying to add a new and quite realistic ingredient to the problem. Is there any way for us to be robust, not only against the possibility that we're badly calibrated on past data, but can we do something that throws the doors open wide enough that we have a decent chance of being well calibrated on future data that might throw us a curveball? And the only really systematic answer to that question is the only way to do that formally and realistically is you have to sit around and think what that curveball might look like. There is no method known to humans, and there never will be, that can protect you against all possible future curveballs that you haven't seen yet. Take the problem of forecasting the price of oil, which came up in that paper I wrote some years ago. If you didn't know much about oil prices, and even if you did, how much probability, prior probability, would you have put on the possibility of the Arab oil embargo back in the 70s before it actually happened? It had never happened before in the history of the world. So people who didn't anticipate it were caught flat-footed when the Arab oil embargo made oil prices shoot up rapidly. And people who had put their position in low oil prices because they didn't see any reason why they were going to shoot up rapidly lost a lot of money as a result of that. Is there any way ahead of time to automatically protect yourself in robustness sense against things that have never happened before? The answer is no, unless you can somehow anticipate what that thing is and include it in your space of possibilities that you're trying to cover your bases over. When I wrote that paper about model uncertainty back in 1995, the end of that paper, you'll see there's a little section called the category other. In other words, wouldn't we like, while we're doing our probabilistic modeling, to reserve a piece of probability for something called other that stands for all the stuff that might happen in the future that we haven't thought of yet? And of course the answer is yes, we would like to do that. But the main operational problem is where do you put that probability chunk and how much probability should you put there? And as soon as you try to answer the first of those questions, you're back to the thing I said before. You have to actually figure out what kind of curveballs the future might show you and try to hedge against them by including them as possible scenarios for what might unfold in the future. Other than that, no one knows how to solve your problem. And in fact, I don't think your problem is solvable, except by the process of trying to think about the potential curveballs and including them in your set of things you want to hedge against. Does that make any sense? Okay. So here's some new R code for us. Let's go ahead and download it. This is the BMA R code now. And I'm going to go ahead and put that on my desktop, for example. That should be around here somewhere. There, it went over there, because there's a hole. I'll fill that hole that way. So let's see what's going on here. This is multiple linear regression. I'm going to use that same attitude data that we were working with last time. You may recall the background, and if not, I'll do a summary of that variable, a description of it for us. So let's start up let's start up a copy of R and see where we get with this. Oops, I didn't want QuickTime. Why did I want QuickTime? No, please. It's because the R icon used to sit right there on my screen where QuickTime is now. Okay, so let's go for R. And let's bring this stuff in. If I remember correctly, last time we had a way to see what was going on with that data. You can use a command called help and name the built-in R data set like that. So let's say help attitude. And we get back to the web, and it says, you may recall from a survey of the clerical employees of a large financial organization, we have data aggregated, in other words, averaged from the questionnaires of about 35 employees in each of 30 different randomly selected departments. So they picked 35 employees at random from each of 30 randomly selected departments within this large organization. And they asked each person whether they would respond yes or no to a series of yes-no questions, such as, does this organization handle employee complaints well? Yes, no. And all the yeses were coded 1, and all the no's were coded 0. And then they averaged the 1s and 0s to get a mean response, a mean positive response in each of those different categories: complaints, privileges, learning, raises, critical, and advance. And then the outcome variable was they also measured an overall rating. So each person was asked to give an overall rating in addition to all these sub-ratings. And now we really ought to have this data at the individual employee level to understand what's really going on, but this data set's not available at that level. If we did, by the way, this would be an interesting data set because it would have a hierarchical character. We would have departments at random, so there'd be random effects for department, and then we'd have employees at random nested inside the departments. So it would be a lot like my quality of care study I told you about, where we choose hospitals at random and then patients nested inside those hospitals at random. And we'd be fitting random effects models in which or what are called mixed models, where we might have both random effects and also what are called fixed effects for covariates at the level of, in this case, at the level of department and also at the level of employee inside department. That's a data set that I would really like to have been able to show you here, but the people, these guys, Chatterjee and Price, didn't let go of that full data set. They just let go of the aggregate data set. So that's our data set. And you may recall last time we ran some code to do Bayesian model averaging. I'll remind you of how that went. First, we fit, I'm back on the part of the web page that shows you the BMS example. First, we looked at the variables to see what their ranges were, and they're all percentages ranging from, I don't know, 30-something up to 90-something. They all have to be numbers between 0 and 100. In fact, you can see in the raw data they were rounded to the nearest integer. There's the entire data set for us right there in front of us. And our goal here is to try to predict the rating column in this data set from all the other 6 columns. And so standard regression modeling, where we think of a linear regression model where each of these complaints and privileges and learning and so on come in with weights that are unknown to create a weighted sum that we use to predict the rating. That's a pretty natural thing to try. And that machinery works best when the variable rating follows the normal distribution well on its own, and all of the predictor variables do as well. And we have a reason to believe that would be true here because all of these numbers are averages across 35 people, and so that'll have a central limiting tendency and make them look more Gaussian. So we ran a bunch of, first I showed you the summaries, then I showed you the correlation matrix, and we noticed that the variable complaints turned out to correlate pretty strongly with the outcome variable, and so did maybe the learning variable, and the other ones didn't look like they had that much to do with it, maybe the privileges variable. And then I did a bunch of QQ plots to show you that all the variables, including the outcome and all the predictors, look pretty close to normal in marginal distribution. And therefore, we can, with pretty much confidence, fit a linear model with the LM command. And the rating is distributed as dot is R's way of saying fit a model in which all the available predictors are used along, and the rating is the outcome. And so it ran ordinary least squares regression, or otherwise equivalent to virtually a maximum likelihood regression with Gaussian error assumptions. And it decided that the variable complaints was statistically significant from a frequentist point of view at a relatively high level. For people who like to look at p-values, the p-value for that one is 0.001 roughly, 0.009. And also there might have been some signal from the learning variable, but its p-value was about 0.07 or so, and people who are strict 0.05 people wouldn't put that variable in the model on those grounds, and nothing else seems to be going on. All right, then we did what frequentists might often do. They would look at that table and say, well, the only variable that really matters here is complaints, and so let's go ahead and fit a regression now in which the rating is predicted only from the complaints variable. And we can plot the results of that as well. We did that last time, and look at the predictions from that as well. And then the rest of it was all Bayesian model averaging. I brought in this package BMS, and I ran the function BMS to produce an outcome data frame called ATT for attitude. And then we looked at various things from a Bayesian point of view, things like what were the posterior inclusion probabilities of each of those variables in all the models that this function BMS looked at. And you can see that that looking at the data, almost all the time the variable complaints came in, but about 40% of the time the learning variable came in, and that's a variable that would have been tossed away as the frequentist tossed them all out approach. And then we looked at some other summaries, and we put a variable in it, and then the next best model has complaints. And then the next best model after that has complaints in learning and advance, and so on. You can see how these things are going. So we have a method for, and also a method for deciding how we might go about creating composite predictions that are based upon averaging over our uncertainty about each of those models. Sorry about this noise. I'm trying to make sure this is still can be heard. And the equation that supports this is right on the next page, I think. You remember on page 33 of part 5, I showed you this equation here that Bayesian model averaging is based upon. It says your overall predictive distribution for future data D star, given the data you've seen so far D, and the background information B, and the fact that you're prepared to condition on a particular subset, script M, of the set of all possible models, is equal to the weighted average of your conditional predictive distributions for the future data given a particular model in that ensemble script M, weighted by the posterior probability model probabilities for those probabilities. So that makes pretty good sense, right? The models that have high posterior model probability end up getting weighted more in the overall aggregate prediction process. So that's Bayesian model averaging in one single equation, and the implementation of that is done by a number of different packages inside CRAN, including this one here, BMS, that we looked at last time, and BMA that we're about to look at today. So now let me go into R and begin running the new code from today. I can again run the summary variable, but I just did that summary command, but I just did that for you. So it turns out that the BMA package requires the predictors to live as a matrix rather than as part of a data frame. And so there's some code here that starts with attach attitude and detach attitude, and then the head command that, that captures the predictors and puts them in a matrix called predictors, so using the as.matrix function in R. And so I'll run those commands. And the head function just shows you by default the first 6 rows in any matrix that you're interested in looking at. So that's a nice thing. So you can look at the first few instances of the thing and see whether it looks like it should be, like it should. Now, I didn't tell you how BMS computed its posterior model probabilities last time, and that's because the author of the BMS package is not very clear on how he or she computes those probabilities. BMA, by contrast, computes those probabilities using a method for model comparison called the Bayesian Information Criterion, BIC for short, and that is one of several possible good methods for choosing amongst models that I'll be talking about later today and or next time. So at one level, I trust the output from this BIC reg in the BMA package more than I do the stuff from the other guy. But the other guy had one advantage. He automatically calculated for us a measure of the model quality, that thing I called the log score last time, and that is not automatically calculated in this world here. So it's good to know about both of them, and also not a bad thing to run them both on a particular data set and see if they're giving more or less the same results, because that gives you a sense of stability. So I run this function, BIC regression, using predictors as my predictor matrix, and the variable attitude dollar rating picks out the rating variable from the data frame attitude. And it ran instantly, as you can see. So with a small number of candidate models, here there's only 6 predictors, and 2 to the 6th is what, 64, I guess, is it? So it isn't very hard to evaluate, do a kind of brute force full enumeration of the quality of all the models. And if I run the summary command now, the BMA software says, all right, well, I've looked at all 64 of your models in this case, and I found 13 of them that look worth keeping. And its basic decision for its way of deciding how many models were worth keeping is it sorts the models on posterior probabilities, and it aggregates from the very first model, then it adds the second one, and the cumulative probability rises, and it keeps adding models until that number reaches a threshold, like 0.95 or something like that. And then it just says, I'm going to pretend that all the other models are negligible, and you can change that threshold if you want. Here, 13 models were chosen, and you can see various summaries that correspond to some of the summaries from last time. BIC reg, the BMA approach, is saying that the probability that this model, that this particular variable, the chance, or rather the posterior probability that this variable should have a coefficient of 0, should not have a coefficient of 0, rather, that's why the exclamation point is in there, is 100% for complaints and about 48% for learning, and the other ones seem to fall off after that. The variable advance comes in with about a 21% probability of not being 0. And we can compare that with the results from, where was that? From BIC, or rather BMS. It was getting posterior inclusion probabilities. It got 0.999 for the complaints variable, 0.9996. That corresponds to 100% over here in this world, so they agree quite well there. It got 0.4056 for the learning variable, and here we're getting about 0.448% or so. It got 0.2129 for the advanced variable, and in the BIC world we're getting about 20.8%, and so on. So qualitatively, the posterior inclusion probabilities are rather similar, and it would be interesting to figure out why they are different based upon the method that was used to approximate the posterior model probabilities, and then to run simulation studies in which you know what the right answer is and see which of these approaches is doing a better job of finding correct signal. Looks like we've reached our first break, so let's take that now, and I'll finish describing this to you when we get back. So I'll start again right at 10:15, and VC Ops, you can turn things off now until 10:15. Thank you. So let's return to the new code, which shows what this version of Bayesian model averaging can do. I should say that what we've just touched on, namely having found 2 different packages inside CRAN, both of which do the exact same thing and come up with somewhat different answers on the same data set. The principal reason for that is that there are a bunch of different methods out there in the literature for approximating these posterior model probabilities. And they turn out to depend on things like not only the prior model probabilities themselves, I'll unpack all of this for you in a little while, but also they depend upon the prior distributions you set on the parameters of all the models that you're comparing as well. And unfortunately, they depend on that in a way that's more sensitive than we would all like. So there's quite a cottage industry in the Bayesian research community filled with people who are trying to come up with better posterior ways to approximate posterior model probabilities for things like this variable selection problem. And I've even joined into the fray. One of my Greek PhD students back when I was in England, and one of his Greek colleagues and I have a paper that is being reviewed now proposing yet another way to do this. So not BIC, we have a way that we think is better. And my first posting after PhD was at the University of Chicago as a postdoc, and there was a lovely man there in those days named Raj Bahadur, who was one of the old school frequentists who did some pioneering work back in the 1950s and 60s on fundamental issues in the frequentist paradigm. And he came from India, as you can hear, in fact from Kolkata, and he used to say that going to the joint statistical meetings reminded him of walking through the market in Kolkata, because all of these different statisticians were all standing there saying the same thing that all the vendors were in the Kolkata market, namely, I have this great idea, buy from me, instead of buying from someone else. And so this little world of all these people who are working on these posterior model probabilities, it's just like the same thing, buy from me, buy from me. And the people who get better market share are the ones who write code and put it in for free in CRAN, and then people start using their code as a result. So if the idea that my Greek friends and I have turns out to work well enough, we should try to increase our market share by putting it in CRAN as well, and then maybe later on, the next time you come back there, you'll see that there's something there by Fouskakis and Soufras and Draper. So we'll see. Anyway, we have a good idea, and we'll see if it's a better idea. So what else do we get from this package here? This one was developed by a long-standing colleague of mine named Adrian Raftery up at the University of Washington, and his students and postdocs and friends. And they were, along with me, among the earliest people to think carefully about issues having to do with model uncertainty. And so I think this package is probably of quite high quality. And there is an argument to be made for using BIC as the way that leads to these posterior model probabilities. So we get things like Model 1 has only complaints in it. Model 2 has only complaints and learning in it, and conditional on those being the only two variables in the model, those are the regression coefficients that they should have. Similarly, Model 3 has both complaints and learning and that variable advance. And so for each one, below it, it says how many predictor variables are there. The first one has 1, the second one has 2, the next one has 3, the fourth one has 2, the fifth one has 2, and so on. Then it says what's the R-squared value for predicting the outcome from this particular combination of predictor variables. And you may recall that R-squared is a standard frequentist measure of linear regression model fit. What you do is you take the observed outcome values, and you calculate the predicted outcome values, and you take those two columns of numbers and calculate the ordinary correlation coefficient between the observed and the predicted values, and you square that. And that's this thing called capital R squared. If the predicted values are really close to the observed ones, then that correlation will be close to 1, and the square of it will still also be rather close to 1. And so we want these R squared numbers to be fairly big. Model 2 has an R squared that's a little bigger. Model 3 has an R squared that's a little bigger yet. But you may recall, if you ever took a regression class from the frequentist point of view, that you can actually make the R squared increase. It can never go down when you add other variables to the regression process. And that means that you could make your R squared look bigger and bigger just by throwing in hundreds or dozens of noise variables. And so to keep that from happening, people in the frequentist world look quite a bit at something called adjusted R squared, which essentially trades off the R squared against a penalty for complexity. And so, in effect, it tempers your enthusiasm for trying to make the R squared big by penalizing you for each new variable that you put in. And in fact, posterior model probabilities do the same thing in an automatic way from a different perspective. So it then calculates these BIC values, and I'll be talking more about that later on. BIC is set up so that large negative values are better than, in other words, you want small values. So minus 30.9 is closer to minus infinity than minus 30.1 is, and so on. So the best model is the one with the smallest BIC, And that turns out to be this one that has only the complaints variable in it. And it achieves a Pasteur model probability of 0.294. I think we can compare that with these numbers down here as well. Somewhere in here there was a table. Oh, yes, there they are. So you see from the other guy's point of view, he agrees the Pasteur model probability of the model that only has the complaints predictor in it is about 0.295, and the BIC story gets virtually the same thing. Then the second model has Pasteur model probability 0.200, whereas this guy's getting 0.167, and so on. So there are some differences between the Pasteur model probabilities, but you notice it starts falling off pretty quickly. We have two numbers in the 0.2s and 3s this time. Then the number drops off to only about 0.09, then about 0.06, and then about 0.06. And what will typically happen is that if we tricked this software into printing all 13 of those numbers, beyond a certain point, they move towards zero in a stubbornly slow manner. And so you end up with many, many models that have non-negligible probability, but not very big Pasteur model probability. And so from a weighted average point of view, they don't contribute very much, and that's part of why the BIC software has decided to stop at the first 13 of them. If we add the 0.294 and the 0.200 and the 0.092 and go out to these first 5 models, looks like we've only got up to about, what, 30, 50, 60, about 72% of the overall Pasteur model probability. And so getting out to model 13 gets that up from 72% to probably about 90 or 95%, and then they draw the line. Well, what else can this software do? It can, if you wanted to compare the regression coefficients with what you would have gotten from ordinary least squares, you can do that. And like it says here on my handout, this produces frequentist ordinary least squares, otherwise known as OLS, estimates for the regression coefficients in all 13 models that were examined by BMA. And you can compare those coefficients with the ones that you see in these models up here to see if they have about the same order of magnitude. Then you can ask it for what the standard errors are of the OLS regression estimates if you wanted to look at them as well. It knows how to compute them also. And the next two commands produce Pasteur means and standard deviations for the regression coefficients averaged over the models with high Pasteur probability. And so I ask it for, please give me BMA.1 Pasteur mean and $ Pasteur standard deviation. And it says, okay, if you make me average over all those good models, I'm going to say that the weight that should be given to the complaints variable, it's a Pasteur distribution with a mean of about 0.7 and a Pasteur standard deviation of about 0.13. So that corresponds to roughly, because remember this is the OLS story, to, in this model here, about 0.75 and an uncertainty band of about 0.097. This is smaller because the frequentist approach isn't propagating uncertainty about the models. Then it's able also to make a little summary if you want to use this to pick out which variables show up. It has a value called BMA1 $which, and which gives a true-false table for which variables appear in each model. And it also shows you some nice plots. If you go ahead and plot, yes, let's plot it in a 3x3 sort of way, because there's 7 coefficients to look at. And so the Pasteur distributions have the following character, which I find criticizable on a particular ground that I'll share with you now. You see that some of the Pasteur distributions here for the different coefficients in the regression just look like ordinary normal distributions or maybe t distributions on 25 or 30 degrees of freedom. But some of them also have heavy vertical spikes in them. And you'll notice if you look at the pictures that all those heavy vertical spikes are at 0. So basically what the BMA people are trying to do is they're trying to give you the following sense. Let's look at the variable called learning, for instance. Basically what this says is that the Pasteur probability that this variable belongs in the model is about 1 minus the height of that particular spike. And so because the spike at 0 means that variable has a coefficient of 0, does not belong in the model. And you can see that number is on the order of 0.5. And so the posterior probability that this variable belongs in the model in some sort of sense in which we're averaging over lots of possibilities is about half. And then the rest of the mass, the other 50%, has been spread continuously over various values that it would have if it were not identically zero. And so as a quick guide to which variables seem to matter, you can look around for variables where for instance, the complaints variable has no such spike at all. That's basically saying that the spike over top of zero for the probability that zero is essentially negligible, and therefore the entire posterior distribution lies to the right of zero. That's what that's trying to say. Yes, please? I would have hoped that the height of that spike would be relevant to things we saw before, and yet I seem to recall that that might not be what we were finding before. Let's see. The posterior inclusion probability for the variable learning, oh yeah, it was about 48%, and that means 48% in, therefore 52% not in, and that spike is right at about 0.52. So that matches the number we had before. If you just regard this as a quick graphical mnemonic for looking at which variables don't belong in the model, that's okay with me, because then you're just going to be having look around for the variables that either have no spike at all, that means they have to be in the model, or quite tall spikes, that means they probably should not be in the model. We're doing weeding out the variables that don't seem to matter. But if you look at the learning posterior distribution and you regard it as a summary of the coefficient on the variable learning, there is something funny about this, because our uncertainty about the outcome variable is continuous, and all of the predictor variables we're treating continuously because they have approximately Gaussian distributions, and the coefficients on them are also things that we have continuous uncertainty about. And yet what this software has produced is some sort of strange hybrid mixed posterior distribution that has a point mass at zero followed by a smooth continuous distribution conditional on not being zero. From a fundamental point of view, that's an odd way to describe how much uncertainty you have about that coefficient. I think you'd agree with me, because it singles out zero as somehow incredibly special compared with the numbers that are only epsilon away from zero, where epsilon could be as small as you like. And you'll see here that it doesn't, in fact, have any behavior that is moving toward the size of the spike at values that are close to zero. It just simply says, I'm going to pick out a singleton on the number line called zero, and I'm going to put a spike there, and then conditional on it not being zero, I'm going to spread the rest of the mass out continuously. Starting with a uniform prior that has point mass at zero and going forward from there is a method that Bayesians call point and slab priors, because the slab corresponds to the uniform part and the point corresponds to the spike. Spike and slab, sometimes called point and slab priors. From a strict point of view having to do with what your actual uncertainty as a Bayesian is about that coefficient, I find that picture disturbing, because we have not treated our uncertainty about that coefficient beta in a smooth manner. And I do know a better way to work with this. It might be beyond the scope of this class, but I'm going to write myself a note to remember to see if we have enough time. Basically, what you can do is you can build a hierarchical model. Instead of making a variable be entirely into the model or entirely out of it, which is what variable selection does, you can have your cake and eat it too by creating models in which each variable continuously comes part way in and part way out. And what you do is you build a model where you have the usual regression structure at the bottom level, and then you put a model on top of the beta parameters, which has a hierarchical character. So you're adding another layer to the hierarchy in which you're modeling the betas in a particular way. I'll write down a shorthand for that model. And if it turns out to be something that people want to hear more about, I can bring work on that to your attention in one of the later meetings. So one of the basic ways to write a regression model, one of the simple ways looks like this: beta 0 plus beta 1 xi1 plus ... down to beta k xik plus ei, as I runs from 1 to n. And the EIs are pretended to be like IID normal draws with a mean 0 and some variance sigma squared E, we could call it, for instance. Um, and the data set that you'd have that on which that would be based would involve a vector y of n observations, and you could collect all the x values into a matrix in which the column called x1 is here, dot, 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 down to the column called k is here. And then to mimic what matrix multiplication does, you could put in a column of all ones to stand for the intercept term. And then multiplied next to that, there would be that vector of regression parameters from beta 0 up to beta k. And then left behind that over here would be those errors, E1 through En. And so look, actually there's a simple way to write the ordinary linear regression model in matrix and vector terms by collecting all the yi's into a vertical vector that's n by 1, and by collecting all the x values into columns of a matrix and adding a column of 1s, because when we do the matrix multiplication, y1 is going to be equal to 1 times beta 0, which picks that one out, plus x11 times beta 1, and so on, picks that one out, and you go all along like that. So this is the predictor part right there. So this part here comes into this particular product, and then the errors are right there. And so a convenient matrix way to, and vector way to write this down is y equals x beta plus e, where y is n by 1, x is n by k plus 1, beta is k plus 1 by 1, and e is n by 1. So this is a pretty standard equation in ordinary regression modeling, linear regression modeling. And a Bayesian hierarchical model would start with that as the one layer of its modeling. And then what you would do to treat your uncertainty about whether variables belong in the model or not in a continuous fashion is you would run another regression in which beta was regressed using a new matrix of z variables times some other coefficients gamma plus some other errors epsilon. And so now we have a matrix that's k plus 1 by, and now you have to figure out how many such predictors there should be. I'll call it p, and this is a p by 1, and then we're going to get over here a k plus 1 by 1. And then you put priors on all the parameters that you see in that model. So this is a hierarchical regression model. And it basically, this matrix here allows you to express information about, prior information about which x's are likely to have big, and then I'll do a plan ahead and go sideways, big and small coefficients. What you do when you do this is it creates a very nice regression situation in which you don't have to decide at all whether a variable belongs all the way in the model or all the way out of it. This second stage hierarchy here will allow predictions which use the x variables in a way that's something like having each x appear on a kind of grayscale somewhere between all the way in always and all the way out always. And these models here end up with posterior distributions on the beta vector that do not have this unpleasant point and curve sort of character, spike and curve character. And they remind me more of what I really understand as a Bayesian is my actual uncertainty about those coefficients. So if anybody's interested in this, I could probably prepare an example of that for a future class. Please drop me an email, and I'll do my best to put something together. I believe I have a data set where I can show you how that goes. This has to be fit with MCMC, but that's no problem these days. Yes, please. It's true that the main applications of this modeling I've seen before have been in epidemiology, where you tend to have relatively small data sets by machine learning standards. And in fact, epidemiology was the field in which I first learned how to appreciate and use these models. If n were on the order of 50,000 here, and k were on the order of 5,000, for example, this would be slow in RJAGs. But we can also parallelize it, like we learned how to do here. So this particular model is not used much by machine learners, who tend to prefer the all in or all out approach. Each submodel has variables that are either all the way in or all the way out, like you saw with Bayesian model averaging. This approach here is not Bayesian model averaging. It's an alternative to Bayesian model averaging that uses each x variable in a grayscale continuous way rather than a series of models, each one of which has each x variable either all the way in or all the way out. And so you can regard this approach here as an alternative to a continuous alternative to Bayesian model averaging. Yes. That's correct. Right. So you build a black box. No one needs to look inside the black box. If it predicts well now and it continues to predict into the future, then you're happy. Yeah, that's right. That's the machine learning perspective. That's right. Correct. About good prediction. That's right. So if that didn't make its way to the mic, and probably it didn't, Tony is talking about contrasting the 2 points of view, one in which you're trying to actually gain structural understanding, in which case it's important that the model be interpretable, versus a different goal of trying to create optimal predictions, in which case the prediction engine might itself be a black box that no one is interested in looking under the lid of, so to speak. Those two goals compete with each other, because it's a basic fact that arises even in the theory that you see when you start working with these model comparison methods, that if you stick within the model class that you're working with and don't go into even weirder model classes like neural networks and blah, blah, and so on, more complicated models tend to predict better. In other words, if your goal is pure prediction accuracy, you will tend to select somewhat more complex models than if your goal is simply to arrive at so-called correct structure. So imagine a world where there is a true data-generating regression model, in which, for instance, in this problem here, variables x1 and x3 and x4 were the actual data-generating variables, and the other three were noise. And you didn't know that. The Wizard of Oz knows that behind the green curtain, right? And the Wizard of Oz throws data over the curtain, and you're trying to figure out what that story was behind the green curtain. If you want a method that, with probability 1, will end up with posterior probability landing completely on the correct data-generating model, that's one way of deciding whether your model's good or not. That's called consistency of your model selection procedure. And BIC achieves that goal, both when the data-generating model, in the situation where you're comparing two models, one of which is simpler than the other, both when the true data-generating model is the simpler one and also when it's the more complicated one. Conversely, if your goal is optimal prediction, then you will end up picking models that are more complex than the ones that BIC chooses, somewhat more complex. And that turns out to be just a completely different goal. And what you end up doing by that means is you end up sacrificing one part of that consistency story. As you move toward more and more data, the methods that are based upon maximizing predictive accuracy have a consistent bias towards slightly more complicated models than are necessary to achieve the full consistency criterion. But in so doing, they produce better predictions than the models that you get solely by BIC. Now, with regard to where the penalty for complexity comes in, there are two places it comes in what I'll be showing you today and next time. And I can actually go back to our basic thing here and show you the formula for BIC, which is later on. We haven't gotten to it yet. But let me show you the formula for BIC. This is on equation 20 on page 54 of part 5 of the organized notes. This says that the BIC value of model J, given the data set D and the background information B, turns out to be the sum of two terms. One of them goes minus twice, and if you look at what's there, it's minus twice the log likelihood evaluated at the maximum likelihood estimate of the parameters. So to explain those symbols for you. So basically you work out minus twice the maximum log likelihood value from model J. That's a measure of how well the model fits, because the better the model fits, the bigger the log likelihood will be. And you trade that off against the second term, which is kj times log n. Kj is the number of predictor variables in the model, the number of parameters that are being used to make predictions. So do you see how the second term penalizes model complexity, and the first term, if it's not good, penalizes model lack of fit? And so BIC automatically trades off lack of fit against complexity. But it does so in a particular way in which the rate at which you're being penalized for complexity is to take the kj number and multiply it by log n. In other words, the bigger the data set you have, the more penalty there is for favoring complex models. See how that comes out with the kj log n term? There's another method called AIC. I think I mentioned that before in the world of people trying to get things named after themselves, that guy Akaike. And Akaike looks exactly like this, except the kj log n term turns out not to depend on n. It's kj times a constant. And so in other words, AIC does not penalize more complex models as the sample size increases. And the qualitative behavior of the kinds of models that are chosen by AIC and BIC is therefore quite different when you start getting into large data sets. BIC tends to favor smaller models. AIC tends to favor bigger models. And that was because when Akaike did it, his sole goal was prediction quality. And so we get back to that dichotomy again. If you're trying to make good predictions, you want bigger models. If you're trying to make sure that your method is so-called consistent, meaning that it will, in the limit with more and more and more data, it will pick out the correct data generating mechanism if there is one, and if it's in the ensemble of things you're choosing among, then you use BIC. And I'll have an argument later today or on Thursday or the next Friday for why that consistency story might not actually be something that you should care about very much, even though there are way people in Bayesian statistics who care about it a lot. Well, but I'm talking actually about better predictions on out-of-sample data. And so you get penalized for overfitting when you try to use the prediction box on new data that wasn't used in the fitting process. And so what happens is AIC and this version DIC and this even better thing called log scores that I'll be telling you about later today, they all have the property that they were tuned in a particular way, not always overtly, but they were tuned to produce good predictions on data not used in the fitting process. And it just turns out that for that purpose, which is different from finding the, quote, right model, you want slightly more complex models. Not so complex as to have overfit, because as you point out, then your predictions will get worse, but enough bigger than the BIC models to do a better job of predicting out-of-sample data. So this is one way right here in which complexity is automatically penalized by Bayesian model comparison methods. Here's another one. I talked, I think, briefly last time about log scores. Let me remind you of the basic idea. We agreed last time that if you have a predictive distribution for a quantity, let's say this is the predictive distribution for observation 6, given the entire data set D and the background information. Yes, thank you. If that's your predictive distribution, and then you can look and see where observation Y6 lands, you now have an interesting problem in which your goal is to compare a single point with an entire predictive distribution for that point. And you have to come up with a number that stands for some measure of how well those two things fit each other, even though one of them is very different than the other. One of them is an infinite dimensional density curve. The other one is just a single point. So how do you create it's called a score. How do you score this particular prediction? By seeing where that Y6 lands in relation to this distribution. Well, you can right away invent some ad hoc criteria. If the Y6 lands close to the middle of this symmetric distribution, then it's a better predictive distribution than if it landed way out in the tails. That makes sense, right? And on that basis, if the predictive distribution were Gaussian, you could invent various ad hoc criteria like creating predictive log scores. This is going to have a predictive mean right there. And so right there, that's the predictive mean for Y6 given the data and the background information. And there's going to be a predictive standard deviation, which is the square root of the predictive variance of Y6 given the data and the background information. And so that allows me, if I want to create standardized scores, like on the z-scale of creating standardized scores, I could go Y6 minus its expectation divided by the square root of its variance. And then you could hope that across all the different points in the data set, those z-scores that result from this, let's call that one z6, you could hope that those z-scores would behave like draws from a standard normal distribution. But that's an ad hoc way to go. People have developed a formal theory of how to do this, and as I think I mentioned last time, without proof, it turns out that all the good scoring rules, when you write down some simple rules that describe how scoring ought to go, are functions of the logarithm of the height of the actual density curve at the point that obtains. And so this gives rise to a criterion that Milovan and I call full sample log scores. So the full sample log score for model J in this simple setting where the data vector just consists of, data set D just consists of the vector Y, Y1 through Yn with no predictor variables and so on. So the full sample log score of model J given the data and the background information turns out to be, well, take the logarithm of the height of the predictive distribution for observation I, and it turns out to not involve cheating except in some interesting, slightly positive way to condition on the entire data set, including observation Yi, and you actually get better discrimination, model discrimination, than if you had left it out in a jackknife sort of sense. So I calculate that for each observation, and I average them. Now, in what way does that distribution, I use that as a model comparison criterion, and I say to myself that M2 is better than M1 if the log score for M2, I'll abbreviate it, the log score for M2 is bigger than the log score for M1, leaving out the other things that are there. Naturally, you want this height to be big because it means your prediction landed somewhere where the predictive density was high, and it turns out to be the right thing to do is to not measure by the height, but by the logarithm of the height. One way I can hand-wavingly motivate that for you is that Bayes' theorem, when expressed on the information scale, can be arrived at by taking the logarithm of both sides. So that log of the posterior density is equal to log of the prior plus log of the sampling distribution. And so taking the logarithm of a density is already a very natural thing to do from a Bayesian point of view when you're measuring information content. And there are other reasons why this is the best thing to do that are less, that are a little bit more opaque. Anyway, how does that criterion? It does not appear to implicitly penalize overcomplexity at all, but it doesn't appear to do so explicitly, but it actually does so implicitly. So now let me draw you PY6 given, actually I should have written D and B and some particular model like MJ, for instance. So I'm going to show you the result for D and B and model 3, where model 3 is an overfit model. Generally what happens when the model's overfit is that you're predicting partly on noise as well as on signal, and that's going to increase the predictive uncertainty bands. And so your predictive distribution is going to be more spread out than it was up here, for example. So its posterior predictive standard deviation is going to be bigger. It might end up having the same mean, but it'll have a bigger standard deviation. And can you see how that penalizes the log score? A bigger standard deviation means what? A lower height. A lower height at the place that the point actually lands. And so we get an implicit built-in, without having to quantify it with something like kj log n, we get an implicit way of penalizing extra complexity through overfitting because your predictive distributions are going to be flatter than they really should be for optimal behavior, because they're going to have larger uncertainty bands than necessary because you put noise variables into the model along with signal variables. And that's going to automatically do the right thing. So, okay. We have wandered off into things that I was going to touch on later on in a more systematic fashion, but that's no bad thing because we're going to come back to them later on anyway. So let's go back now to what's going on here and see if there's any other interesting stuff we can wring out of this software, and I believe the answer is no. I just basically said down at the bottom of this file, the function bic.glm is available in the Bayesian model averaging package, the BMA package. And here we were using it for linear regression models. So the function we used was called BICREG. You may remember up here, BICREG. But they have another function which works in what's called generalized linear models. And they are models that include things like logistic regression with dichotomous outcomes. If you have a yes-no predictor, which would in machine learning be called a classification problem rather than a regression problem, it's really also a regression problem in disguise where the outcome variable is dichotomous. Or it might be a categorical variable with more than 2 levels, but let's just talk about 2 levels at the moment, yes-no, for instance. It also knows how to do Bayesian model averaging in models like that, and I'll give an example of that next week. I'm going to show you some logistic regression models next week. And you can go look, and you'll find that there's another package called BAS, and there's another one called Ensemble BMA, and we could go on for many hours talking about all the different buy for me sort of ways there are to try to do this, but you get the flavor of it. The thing that's good about the BMA package in compared with the BMS package is that the BMA package is based on BIC, which I think is a good way to compare models from at least one particular criterion. I'm not sure what the other guy is doing. I think he's using things called G-priors, Zellner's G-priors, involving some unit information idea, and that has the flavor of what my student Dimitris and I were trying to do. I'm not sure if he did it in the best way possible. I don't know. But this BIC package, the BMA BIC stuff, has the disadvantage that as it's currently set up, it does not give you the information you need to be able to compute log scores. So you can't actually compare the log score of the Bayesian model averaged models with the log score of the model that you get just by picking the most likely model, for instance. And again, I'm going to try to prepare an example for you for next week that will show how that goes. So that's been another little touch of stuff having to do with Bayesian model averaging, and it completes most, at least, of the formal stuff. I'm going to be showing you about that, and there, as I say, there might be another example next week with dichotomous outcomes, or maybe with a much more interesting regression data set. Yes, please. Do you mean when the predictor variable is itself a nonlinear function, like x squared rather than x, and so on? Yes, it has no trouble with that. You just have to build the X matrix to include columns that are nonlinear functions of the original variables, and then they come in as additional predictors. That's correct. That's correct. So we've talked quite a bit now, yet last time and today, about Bayesian model averaging. Let's talk for a while about Bayesian nonparametrics. We talked a little bit about this last time. I showed you that De Finetti, or I mentioned to you that De Finetti proved another theorem, even more fundamental than the one that we looked at before for binary outcomes, the one at the top of page 35 in part 5 here, that says if your uncertainty about some real valued yi's is exchangeable, then in effect you are essentially behaving according to that hierarchical model at the top of page 35. And it says, think about, take your y1, y2, ... and extend it out to just what I said. You got y1 through y little n, for example. Extend it all the way out to y1 to y capital N if there's a finite population you're trying to learn about, or extend it out y1, y2, ... to some countable collection if your population is bigger than that. And if your judgment of uncertainty extends outward from the sample you have to that bigger world, which, as we have said before, is like thinking of your data set as like a random sample from the population. And in this little Kaiser example on page 34, it was literally a random sample from this population. So if that's true, that your judgment of exchangeability extends from your uncertainty in the data values in the data set you're going to see to all the data values in the population you're trying to learn about, then collect all those yi values in the population together and construct a cumulative distribution function from them. Let's call that thing capital F. And the hierarchical model says, if you know what capital F was, you can treat the yi's as IID given F. But then to be fully careful about your uncertainty from a Bayesian point of view, you have to be prepared to place a prior on capital F itself. And as we began to talk about last time, this has to be a harder thing than anything we've talked about so far in this class, because so far we know how to put priors on numbers. And that's really all we've done so far. We've treated, even when we had a vector parameter, theta, consisting of different components, we put a series of marginal univariate priors on all the components of it. So we haven't even gotten in this class to the process of putting priors on vectors. For example, you might put a multivariate normal prior on a vector rather than putting a univariate normal prior on a single scalar that was a part of a vector, for instance. People have developed methods for putting prior distributions on certain kinds of matrices as well. But all of those things are finite dimensional quantities. You have a scalar, dimension 1, you have a vector, dimension k, whatever you're working with, finite dimensional. Capital F is a very high dimensional thing if you're going to try to think of the model as one where your uncertainty about the yi's is continuous. In fact, it's an infinite dimensional thing. In fact, for people who like to think of orders of infinity, it's an uncountably infinite dimensional thing. It's just a very, very complicated object. Now, the process of measuring anything in the world, as we've discussed before, inherently discretizes it. When you're weighing something, for example, I go to a market near my house called New Leaf, and I say, that piece of Pacific Soul looks pretty good, I'll have it. And the guy puts it on the scale, and it rounds the weight to the nearest hundredth of a pound. That's just the way his scale works. And so I don't really have to treat weight as a continuous quantity, because actually it comes out in units of a hundredth of a pound. And if I had a cruder measuring instrument, it would only come out in tenths of a pound, for example. And if I had a better one, it would come out in thousandths of a pound. You can see how that goes. So strictly speaking, we probably don't need an infinite set of dimensions to model what's going on. But if we tried to treat it discretely, we would find that we had a finite story with a really, really, really big number of possibilities. Because as soon as you take 1,000 values for y1 and 1,000 values for y2, and you begin crossing them against each other, you have really big possibilities, right? So we often use continuous models as nice, we hope, mathematically tractable approximations to a discrete reality. That's basically when we talk about our uncertainty about some y's, like the weight of my piece of Pacific Soul. We talk about modeling that uncertainty continuously. We're using an abstraction, really, because you can't actually attain that ideal. Nevertheless, it would be good if we could to be able to build prior distributions on CDFs that could somehow, in principle at least, approach that goal of treating F as a continuous thing, because then if it really were discrete, that would just be a special case. So that's what people have tried to do. And there are two classes of priors so far. They're called Dirichlet process priors and also Pauly-Treat priors. And I think I'll take a break now and begin showing you some of the code in which I worked out some examples for you of each of those. It turns out actually that Dirichlet process priors are special cases of Pauly trees. But since they're different enough special cases, people continue to use the two different names. It's almost like the same thing that happens in MCMC. Gibbs sampling is actually a special case of Metropolis Hastings sampling, but it's a different enough special case that people talk about Gibbs sampling as a separate object. We could really call all of it Metropolis Hastings sampling, but actually Gibbs sampling as a special case is worth its own name. And the same thing happens with these so-called DP priors. So for this purpose, I'd like to go into, let's see what this one is here. I've given you some new things called Part 6, Section 1, and Part 6, Section 2 on Bayesian nonparametric modeling. Let's start in on them now. And by the end of this stuff here, we will have known something about how to build Bayesian nonparametric priors. Yes, please. Yes. That were deeply uninterpretable. That's true. Um, and that would be part of the process of training the robot to be useful to us. Um, if no one knew about neural networks and the robot somehow discovered a neural network and and showed you that that was a model that seemed to predict very well, for example, and it was a god-awful mess. The robot said, I don't know, it's really hard to describe this to you, but this is what I did last night while you were sleeping, and this is actually a great model. It's the best model it's better than any of the models you gave me, and it's also better than any of the ones I found. There might be some value for looking at those really complex, weird models that a robot would give you and seeing if they can parse in some way. But the other way to go, of course, would be to put some kind of interpretability penalty on the robot and say to the robot, these are the only kinds of models that we humans understand at present. Would you please tell me about good models within that restricted class? And then you might be able to make progress still. Good point. So we're back in the situation where we've got De Finetti's theorem. So just as before, suppose in the future, I'm now on page 2, I think, of part 6, section 1 of the organized lecture notes. And so reminding you of the setup here. Suppose in the future I'll observe real valued y, y1 through yn, and I have no covariate information so that my uncertainty about the y's is exchangeable. As before, we're going to build up to more complex models by starting with simple data sets that are just single columns of numbers, real numbers, and then later on we'll start adding covariates like we did in the regression example, and we'll be doing in other examples as well. Then, if I'm willing to regard that data vector of n observables as part of an infinitely exchangeable sequence, which is, as we've said, like thinking of the y's as having been randomly sampled from the population, then to be logically internally consistent, or what De Finetti called coherent, I have to be able to express my joint predictive distribution in a particular hierarchical form in which I have to be prepared to place a prior P of f on the space of all possible cumulative distribution functions. So, to sneak up on the way Dirichlet processes work, I want to talk a little bit about the bootstrap first. Have we talked about the bootstrap in here? I think we have not. This is a frequentist technique that, in my view, serves as some kind of useful bridge between the fully frequentist story and the fully Bayesian story. So it's worth knowing about from a variety of points of view, including a Bayesian point of view. So you may recall that quite a while ago, toward the beginning of what we were doing, I drew a picture that was a kind of complicated looking diagram with 3 columns in it. There was the population data set and the sample data set and the imaginary data set. And these all represented different things that were crucial in understanding how Mr. Neyman thought about probabilities. And I'm trying to find that page because it would save me time in having to draw it again. But it's looking like, and this is definitely something, another plan ahead. I should have done this during the last break. But I don't, oh, there it is. Bada bing. So all those weeks ago, when we first started talking about the heart attack mortality case study, we got from each person, the sample consisted of the observed patients, and the outcome variable was whether the person died or not within 30 days of admission. You remember this example a long time ago. It was our first simplest example. It was our second one. The ELISA HIV example was the first one. So we have 400 ones and zeros, and we got the mean, p hat or theta hat. And to infer outwards from this data set back to the population that these people are like a random sample from, we have to first say who that is and then think of the data set as either actually an IID sample from that population or like an IID sample. Once you've identified the population, it will be some much bigger data set, capital N rows in it, for example, And if you could dump all them out and take the mean of the ones and zeros over here, that would be some number theta, and we just don't happen to know that number. So this is the basic inferential story. And we're going to try to use the data in the sample to estimate this theta over here. For example, by using the simple principle that the sample mean should be a good guess for the population mean if the sampling is good. And IID sampling, we agreed weeks ago, is a good way to sample from a population. Now, from the frequentist perspective, even though I have only one data set, to know how good that particular p hat or theta hat is, let's call it theta hat, to know how good that theta hat is as a guess for theta, you recall that we had to do this funny dodge. We had to say, because our notion of probability from the frequentist point of view is based solely upon repeating something, we have to imagine the process that gave rise to that theta hat occurring more than once. So even though we're only going to really see one data set with 400 people in it, that's called the actual sample. In order to see from a frequentist point of view how good this particular theta hat is at guessing at the true theta, we have to imagine other data sets. Remember that trick? So this is where the frequentist thing comes in. You imagine a hypothetical IID sample of the same size, namely 400, and you get a theta hat from it, but this one is question mark because we haven't done it yet. We're just thinking about what you might get. This time we got 0.18. Next time you might get 0.20. Do it again. Next time you might get 0.17. Do it again, do it again, do it a lot, and collect all the theta hats together into this data set over here, which I called the repeated sampling data set. And if I let the number of rows in the repeated sampling data set go to infinity, I would eventually collect all possible thetas right here. And then it's quite interesting to talk about what's the long-run mean of those theta hats, what's the long-run standard deviation of them, which we call the standard error, and what does the long-run distribution of those theta hats look like. So the guy who invented the bootstrap is a great statistician at Stanford named Brad Efron. And I don't think that Brad had this picture in mind, but I'm now going to describe the bootstrap to you as if he did have this picture in mind. And I should say that in some sense, if I had been paying attention and gotten luckier to get into statistics a few years before I did, I might have been right up there with Brad trying to invent this thing with him, because I graduated from PhD study in 1981, and Brad published his first paper on the bootstrap in 1979. And during my postdoc at Chicago, I created this diagram as a way of helping people understand the frequentist story. If I had created this diagram 10 years before that, or even only 8 years before, something like that, around the year 1975 or so, then I would have had a chance to invent the bootstrap too. And you can help me invent the bootstrap now with this picture. Efron says to himself, well, this is great, except you don't know what the population is. So what would happen, just let's find out, what would happen if I did what the old computer scientists called a shift left logical, and I moved the sample over into the place that the population has. And now I continue the rest of the logic of the diagram. Why would you want to do that? Well, we said already that the IID sampling is a good way to get a representative sample of the population, meaning that that sample should be good, a good reflection of what the population looks like. So let's temporarily pretend, for the sake of this bootstrap idea, that the sample is the population. So grab the sample and move it over into the population part of the diagram. Now, Efron says, follow the rest of the logic here. Now take a hypothetical sample from your sample and do that again and do that again, and collect the results over here in this repeated sampling data set. Well, right away, you have two questions from an implementation point of view. How big should each of those random samples from your sample be? And secondly, should they be made at random with replacement, which is IID, or at random without replacement, which is simple random sampling? Now, to answer the first of those questions first, Efron said, again, just to see where this leads, let me make each of these samples here from your sample be of the same size as the sample itself is. So I'm going to have a fake population over here of size little n. The part that has the capital N and all this theta stuff, it's all disappeared now, and I just took this part and moved it over here, pretended it was the population. What would happen if I chose little n observations at random without replacement from little n observations? What would happen? The first data set I got would bear what relation to the sample? it would be identical to it. The second time I did it, I'd get the same data set, and so on. So having answered his first question, that I want little n guys in this sample to correspond to a sample size little n from my original sample, I have to do the sampling at random with replacement in order to get meaningful variation. And so that's what Efren did. As a by the way, people have since then tried to say, well, is there any advantage of having these things called the bootstrap samples be either bigger or smaller than the original sample size? And the answer turned out to be sort of no, really not much in it. So let's go with what he says. Let's stick with little n equals 400 in each of these data sets. By the way, the same way we did here, except now the population also has 400 elements in it. And now we're literally, and this sounds kind of strange, we're literally resampling at random with replacement from the sample. Whatever the number y1 is in the sample, could it appear in the first resample? Could it appear by random sampling? Well, sure. Could it even appear more than once? Yes, it could. Then that's true of every single observation. So when you're done, each bootstrap sample consists of all of the things that were in your actual sample simply repeated a random number of times, where the random number is either 0 or 1 or 2 or so on. And in fact, that random number of times turns out to follow the so-called multinomial distribution, because each observation in the original sample, if all the observations have unique values, each observation is itself acting like a little category, and you're asking how many times do I get things from that category over and over again. That's multinomial, right? That's how the multinomial works. So he was able to use the theory of the multinomial distribution to show that what I'm about to describe to you now is a good idea theoretically. That was essentially what he did. So now let me sketch what the new diagram looks like. It looks just like the old one, except we do this weird move in which we replace the population with the sample. So this is now the bootstrap. I need to switch over, don't I? No, I've already switched, okay. This is now the bootstrap diagram, as distinct from Mr. Neyman's diagram, or my version of what Neyman was thinking. So now we have the sample over here in the place of what the population is, and so it's just our data set y1 down to yn. It has n observations in it. And by the way, it has a sample estimate, which we could call theta hat. Now we're going to create a thing called bootstrap resamples. And we're going to create lots of them. So the first one is an IID sample, also of size n, from the data set. The second one has the same exact character, and dot, 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 down to the last one has the same exact character. Will I get the same theta hat in the first bootstrap resample that I got on the whole data set? Theta hat is just something I got by making doing something to the numbers y1 through yn. If I'm resampling with replacement from those y1 through yns, I can apply that same mechanism to get a theta hat, but will it be the same theta hat every time? No. And we don't want it to, because the way these theta hats over here are varying is going to tell us a lot about how good theta hat is as a guess for theta, it turns out. So here I'm going to get something called estimate theta hat 1 star, estimate theta hat 2 star, dot, 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 down to estimate theta hat capital M star. And now following the same logic of my picture before, we're still going to have something that behaves like the repeated sampling data set, but now it's going to be the bootstrap data set of theta hat star values. So I take this one and I put it there, and I take this one and I put it there, I take that one and I put it there. And just as before, capital M is the number of rows here, and I want capital M to go to infinity to really see what's going on. In practice, of course, you're going to do this with your computer, and so you can't let M go to infinity. You can't let it go to infinity, but you make M some big number. And in examples I could show you, when Efren first did this stuff, and it's quite interesting, there's a natural parallel with what went on with MCMC. When MCMC was first introduced to statisticians, around the year 1999, it was exactly the right moment for the Gibbs sampling algorithm to be just fast enough so that people's desktop machines in their offices could get a good answer, a pretty good accurate answer overnight. And now roll the clock back 20 years to 1979, possibly by coincidence, but perhaps not. Efron's bootstrap procedure had the same property, that as long as you chose a value of m that was big enough to be able to make a run overnight on the desktop computers of that day, you could still get a pretty good idea of what's going on. But here's the difference. In 1979, that number was 500 for even rather simple functions over here. And today, that number is more like 100,000, maybe even a million, depending on how much accuracy you need. And I see that we've reached our second break for the morning, so let's stop, and I'll start again at 11:30.